Good morning, ladies and gentlemen. I'm Cadet Abigail Gash, and this is Cadet Shelby Allen from the United States Military Academy, and this is our presentation on quantifying the water demand with the use of cementitious or supplementary cementitious materials.
So our research question is, how can we quantify the change in water demand in relation to the percent replacement of Portland cement with supplementary cementitious materials, or also known as SCMs, which we will refer to it as in the rest of this brief, with silica fume and fly ash. So some of the why behind this research is the industry is trying to look for every way to make a green concrete, a sustainable concrete, and cement is known to give off a ton of CO2 emissions, which we're trying to reduce throughout this research. And we originally started out our research last semester by making a complete 0% concrete mix with 5 different SCMs of silica fume, fly ash, metakaolin, slag, and hydrated lime. And some of the issues we saw with this were that we didn't know the water demand of each SCM, which caused us to add more water throughout the mixing process. And so that led us to our new research question of trying to quantify the demand in certain SCMs before moving forward to a complete 0% concrete mix. So we'll do this by making a constant 4-inch slump to measure the workability of each mix, and this will just be constant throughout all of our mixes.
So we focused on fly ash and silica fume, being that they're both most commonly used in industry right now, as well as their industrial byproducts. Fly ash being the industrial byproduct of pulverized coal, and silica fume being the industrial byproduct of electric arc furnaces. Current research on silica fume has shown the property, or has shown in concrete, has shown the effect of the concrete as shown, and then we'd like to highlight the increase in water demand.
So our first step in methodology is going to be classifying our constituents. With our coarse aggregates, we're going to do a gradation test and a specific gravity test, which are going to make constant, it's going to be a consistent coarse aggregate throughout each of our mixes, and it's just to ensure uniformity throughout our mixes, which is according to ASTM standard. And we're also going to classify our cementitious materials with silica fume and Portland cement, which are also according to ASTM standard.
So the second step in our methodology was the batching. We started with the coarse aggregate and 50% of the estimated water and mixed for 2 minutes. Then we added the fine aggregates and 25% more of the estimated water and mixed for 2 more minutes. Then we added the cementitious materials and mixed for 10 minutes. We let the mix rest for 3 minutes, and then we added water as needed for the final 10 minutes. And then we conducted slump tests to make sure that we were meeting the 4-inch slump. For all tests, we recorded the slump and then the water that was currently in the mix. And if the slump was less than 4 inches, we added water and mixed for 3 more minutes. If the slump was greater than 4 inches, then we added 10% of all the constituents by volume and then mixed for 3 more minutes.
So step 3 in our methodology was curing. We let our concrete cylinders sit in the plastic molds for about 24 hours, and once the 24 hours had elapsed, we removed them from their plastic molds and decided to do a wet cure with them. So we emplaced each of our concrete cylinders in different sections according to the mix and percent replacement, and it sat in the curing tank with a constant temperature of 20 degrees Celsius, plus or minus 2 degrees. And then once the wet cure was done, we did our concrete testing, which was a compressive strength test at the 3, 7, and 28-day mark, a split tensile test at the 7 and 28-day mark, and a durability test with the fresh mix and the 3, 7, 21, and 28-day marks, all according to ASTM standard.
So currently in the study, we've done the control and the silica fume mixes of 2%, 4%, 6%, 8%, and 10% replacement. And then in the future, we'd like to do fly ash with 5%, 10%, 20%, 30%, 40%, being that fly ash has a higher percent replacement. And then we've done the testing for the control and silica fume mixes as well, and we're pending 28-day testing, as well as we've done the compressive split tensile and durability tests.
So now we will look at the water demand versus the percent replacement. So we can see on the 0% replacement, we have our control mix of just our regular cement mix. And throughout each percent replacement from 2 to 10, we were able to make a logarithmic equation. However, we'd like to note that the 8% replacement was not included in this logarithmic equation, as it appears to be an outlier.
So for our 6%, 8%, and 10% replacement mixes, we recorded the water to cementitious material ratio against the slump in inches, and found that there's actually a linear relationship between the slump and water to cementitious material, which led us to finding an initial empirical equation. The average slope between all three mixes being 0.0125, and the intercept actually varies, so our initial equation is y equals 0.0125x plus b.
So now looking at our step 4 methodology, we're looking at our concrete testing, which our first test was compressive strength versus age. We can see that the 10% replacement had a 10% increase compared to the rest of the percent replacements, which is around 2,000 psi of an increase. And we can also see here that our initial strength gain was not what we had initially expected, as they are all lower, or the 6% was equal to our control mixture, which we had hoped that the initial strength gain would have been higher than our control mix.
So this is our 7-day split tensile test. Here we'd like to highlight that there was a decrease in the tensile strength as the percent replacement increased. Again, noting that 8% we highlighted as a outlier, as it didn't decrease following the pattern. So then we also conducted the durability test via an electrical resistivity. This test is significant because lower resistivity means that there's a higher chloride penetration, which is then harmful to the reinforcement. So we found that the resistivity actually increased as the percent replacement increased, as well as the resistivity increased as the concrete aged. So here we have the 0, 3, 4, 7, and 21-day strengths of the control 2%, 4%, and 6% mixes, and the linear relationship as they increased. And the lines are denoting that they're getting more into more significant resistivity, so less chloride penetration.
So in conclusion, we can see that some of our preliminary findings aligned with expected behavior, as in the silica fume increased as we increased the water, or as we increased the percent replacement in silica fume, the water demand increased. We had a higher higher replacement in mixes were qualitatively less workable. We increased resistivity in higher replacements, which was our increased durability, and we found our empirical formula of y equals 0.125x plus b. And some of our preliminary findings that were not expected were the decrease in compressive and tensile strength, which we looked at how we thought there was going to be an initial strength gain.
So for future research, we'd like to retest 8% as it was an outlier, and then we'd also like to collect more data on the water demand change in a mortar, and then the VICAT test for the initial and final set time with the percent replacements, as well as a flow test to test the mortar workability. We'd like to do all of these tests again with fly ash, again the 5%, 10%, 20%, and 30%, and 40% replacement. And then we'd like to in the future do a ternary blend. So understanding the impact of the water demand and the known replacements on the binary blends to then begin experimenting with a ternary blend and the impact of the water demand of known replacement percentages of both fly ash and silica fume combined. Ladies and gentlemen, this concludes our presentation, pending any questions.